Welcome. So now we're going to be writing the equations of radical functions given a graph. So you want to identify your key point. It's a starting point for square root, or it's the middle value in the row of 3 for the cube root. That's the best description I can give you. And by the way, this is in your notes. So remember, we always see those 3 points that go together in the cube root. Right? It's that middle value. That's going to be your key point. You're going to substitute this value for h of k in the general equation for square root, and choose any point x, y, and solve for a. We are going to stick to solving for a most of the time, unless we'll do b just a little bit. It's okay, I'll do b if it's a description, but for the graph, we'll mostly just solve for a, but we will solve once in a while. And I think once you see the graphs, I think you'll figure out when we're solving for b. So f of x equals the square, a times, put this in your notes, you have this blank space in your notes there, f of x equals a times the square root b times x minus h plus k. So even if we don't have, even if we're not solving for b, in other words, even if b is 1, we still want to remember the correct form of the equation, because once in a while we'll solve for b. And then the cube root is the exact same thing, except put a little 3 on your radical, x minus h, oops, there we go, and then plus k. All right, so that's the general form of our square root and cube root. And so we're going to be solving for a, right? And I will tell you when you might be solving for b. All right, so we're going to fill in, once you found a, and I do want you to solve for it. Once you find a, you can fill in a, h, and k in the general equation. You can fill in b too, but b is going to be 1 most of the time. To check your answers, you can superimpose the graph of y equals the square root of x, or the cube root of x. I left that out. So you might want to add that to your notes. And compare corresponding distances to determine the factor by which the function has been stretched, or if the graph has been reflected. We'll use this technique if we need to solve for b instead of a. Right, but I will keep it simpler when we're solving for b, because it is a little trickier being inside the radical and all. The first one is in your notes and it's all up. Right? So I'm going to go through the steps, and then we're going to do it again with 2 different points. All right, so you're using a point to solve for a. Right, so our general form. Oh, and I left the parentheses off. Oh, shame on me. Shame on me. We saw that in the last video what we'd have to do. Makes the h harder to find, right? So if you would just, I'll do it in black. If you wouldn't mind, you have this in your notes, just please add parentheses, right? The parentheses right there, all right? Around the x and the h, right? We'll just be in a good habit. I guess maybe we don't need it if we're just solving for a and we know b is 1, all right? But when we're solving for b, I guess we can leave them off here. I guess I'm okay with it because we didn't write b in, right? But later on, we might solve for b, and so then we want to remember that if b is not 1, then we do need these parentheses. We'll just do that. Okay, so if we're solving for a, if we're solving for b. All right, so we're just actually solving for a. So that's why I left the parentheses off. All right, so hk is your starting point of the square root function. Xy is any other point on the square, and it really doesn't matter which one. All right, so hk does matter. This is hk, all right? Notice it's the starting point. How do you know it's the starting point? Because the function is going the other way, and that's where it started. All right, xy is any other point. In this one, I used 5, 5 as the xy, so we'll look at this point first, right? And then we'll look at using another point. Right? So we have 5, because that's y. 5 is equal to a times, we plug in for x, 5. H is 4, so 5 minus 4, square root of 5 minus 4, and then k was 2, so plus 2. And then we just simplify. Right? So 5 equals a times 5 minus 4 is 1. Square root of 1 is just 1, so we have 5 equals a plus 2. Solve for a, subtract 2 from both sides. So y equals 3 times the square root of x minus 4 plus 2. No need for parentheses because b is 1. Right? And in these ones, b is going to be 1. These aren't horizontally stretched or compressed. Right? They're not going to be growing faster or slower horizontally. I will tell you if they are. All right, so I'll make it really, really obvious. All right, so now let's do the same thing, but now let's just use a different point. So we use this as the x, y. All right, so we have 8 equals the square root, or 8 times, the square root of x is 8. So 8 minus, and then h was 4, and then plus 2. So we have 8 equals a times the square root of 4 plus 2. Right? And so take the square root of 4, it's going to be 2. 8 equals 2a plus 2. Subtract 2 from both sides. 6 equals 2a, and then divide by 2. Right? 3 is equal to a. Right? And you get the exact same a value. Right? And then we would just plug in the a, the h, and the k. Right? And that's all there is to it. And you might wonder what happens if I don't get a perfect square. Well, if x and y are if everything is integer values, h and k and x and y, you should be getting perfect squares. Whatever's under the radical should be a perfect square, because when you evaluated a times h minus square root of h minus k, or when you evaluated a times the square root of x minus h plus k, this part here, you get y. And if y is an integer, then whatever was under the radical has got to be integer too. All right? So these should all be perfect squares. All right, so let's look at the second one. All right, so here's our starting point right there. That would be our hk. And then xy that was used was negative 2, 6. So we have negative 6 equals a times, we plug in negative 2 for x, negative 2 minus a negative 3, right, because it's minus h. So if h is negative, then we have minus a negative, and then plus negative 4, because k is negative. So then we simplify that. Negative 6 is equal to a times negative 2 plus 3. And negative 2 plus 3 is 1, and the square root of 1 is 1. So we have negative 6 equals a plus negative 4. Add 4 to both sides, and a is equal to negative 2. Y equals negative 2 times the square root of x plus 3 minus 4. And that makes sense that that should be negative, because notice it's reflected across the x-axis. Right? It's down below the x-axis, not above. Let's do the same thing, but this time we'll use another point. This point here looks like a good point. Right, that point there is 1, negative 8, and that's going to be our hk. Now actually, if we don't like that one, we got several up here. We can also take this point. They're kind enough to put lots of points on there. And we can use that one. That point there is 6, negative 10. They're very nice and generous on the points. And it's supposed to be a comma. That doesn't really look like a comma. All right, so 6, negative 10. All right, so we just plug in. So we have negative 10, that's y, right, is equal to a times the square root of 6 minus a negative 3, and then minus 4. So we have negative 10 equals a times, minus and negative is plus. This is 6 plus 3. Add 6 plus 3 is 9. And the square root of 9 is 3, so we have negative 10 equals 3a minus 4. We'll add 4 to both sides, so negative 6 equals 3a. And then if we divide both sides by 3, hopefully you can see this, I'm squeezing it in there, negative 2 equals a. There we go, exact same answer as before. See, so there's a relationship. That relationship holds true for any pair of points on this function. It doesn't matter which points you use, just that x and y and h and k have to be different. Can't use the same point twice. All right, and that's all there is to it. Let's do a few more, though, that don't have the steps up. Right? So, by the way, you should write in the additional ones that we've used so that you can see again how to solve it, and you can see it doesn't matter what point you use, so long as you're not approximating your point. All right, so let's use this one here. All right, so here's our hk. And so that's the point negative 1, 1. And then, well, here's a good xy. They put a big old dot on it, right? I should probably use that one. All right, so here's our x, y. There looks like there's other good points. Looks like 8, 4 is a good point as well. But 3, 5, 3, 3 has a big old dot on it. So let's use 3, 3. All right, so we have y equals a times the square root, and technically it would be b times x minus h plus k. Right? But I'm going to tell you that b is 1 in this problem. Right? If your graph looks super skinny, you might look to see if it's b. Sometimes we can get the same effect. One b value and a different a value might give the graph the same effect. So we try to write our graphs using a, however, solving for a, but sometimes we'll have to solve for b. But I'll make it obvious, like I said. All right, so we have 3 equals a times the square root, and of course our b, is, I said, is going to be 1. So we're just going to need x, so x is also 3, and then minus a negative 1 plus, and k is 1. All right, so we just plugged in. Plug and chug, and now it's just a little simplifying. So easy as this. 3 equals a times, that's going to be 3 plus 1 plus 1. So this is 3 times a, that's the square root of 4. Square root of 4 is 2, so that's 2a. Subtract 1 from both sides, 2 is 2a. All right, so that means if we divide by 2, that 1 is equal to a. So not only is b equal to 1, a was equal to 1 as well. All right, so we already identified h and k, so we can write the equation. Y or f of x, whichever you prefer. Y is equal to, you don't have to put the 1 in there, the square root, and you don't have to put the 1 for the b. X minus a negative 1 is going to be plus 1, right? It's the same thing as we had up here. And then plus 1, and there we go. We've done it. See, easy, cheesy, lemon squeezy. But if it's not easy, cheesy, lemon squeezy to you, then ask me, and we'll go over them again, okay? Or I can do more examples, right? Let's do another one. I don't know. I think I have maybe 2 more, maybe 3 more. I promised one that was a b. And at least one's a cube root. All right, so we want to write the equation of the graph here. They don't put any nice points on us for us, but I think we can see a few clearly. That's a good choice. And that's a good choice. All right, so that point there is negative 1 and, excuse me, positive 1, negative 2. And this point here is 1, 2, 3, 4, 5. So 5, 0. I think that's a good point to use, right? This one over here looks like a good point, right? Only integer values, no approximations, no kind of closes, right? Only integers. All right, so this is a square root. So we have, let's do f of x. F of x equals a times the square root of b times x minus 8. And I think most of these are in your notes, by the way. Oops. And just ignore that. I must have quadratics on my head. And I meant to write x. X, not h minus h. X minus, oops, we forgot b now. Let's try that again. I think the heat is getting to me. Air conditioning still broke, class. So a times the square root of b times x minus h. There we go, plus k. All right, so now we need to plug in, and of course f of x is the same as y, right? So we have, this is our xy, a lovely pair of points, and this is our hk. All right, so we have 0 equals a times the square root, and b is going to be 1. I'm going to tell you right now. Because it would be a lot harder, if you had to solve for a and b, you couldn't do that necessarily with one equation, right? Unless you looked at the graph, how it changed, right, from the parent function. And we'll look at that as well on this graph. I'll just kind of compare it. Right? This graph's a little easier to compare to the parent function. So we have 0 equals a. B is going to be 1. Right? So I'm going to tell you you're not solving for b here. right? And then our x is 5, and our k would be minus, hold on, did I misidentify a point? So wait, 1, 2, 3, 4, 5, yeah. And that, oh, why did I put negative 1? Did I do that twice? 1, negative 2 is HK. I don't know why. Crazy come the heat, I guess. All right. All right, but at least I realized there was a problem. All right, so we have x minus h. That point there is 1, negative 2. I keep wanting to put the negative, switch my negatives. So 5 minus 1, and then plus a negative 2, or minus 2, whichever you like. I'm going to write that clear. I think the negative kind of is getting lost here. All right, so we have 0 equals a, and then 5 minus 1 is 4, and then minus 2. Square root of 4 is 2, so 0 equals 2a minus 2. Add 2 to both sides, right? So 2 equals 2a, and then divide both sides by 2. 1 is a, and so we don't need to plug in 1 for a, or a for, yeah, 1 for a. So we can just write our equation, y or f of x, whichever. Y equals the square root, right, because a was 1, b was 1, of x, and then minus 1, and then minus 2. And there's our equation. So when a is equal to 1, it's a little easier to see what the equation is, because this will have the exact same shape. Right? So here's the parent graph, right? 0, 0, 1, 1, 2, 3, 4, 2, and then 3, 4, 5, 6, 7, 8, 9. Right? So here, if you compare the rate of change horizontally and vertically, right? So 1, 1, 1 and 1, and 4 and 2, and 4 and 2, and so forth. Right? But I want you to be able to solve for a, but you should also be able to look back and say, yeah, I agree with my answer. Because sometimes what looks nice and easy might not be. Right? For instance, what if the scale was changed? So you're looking, yep, that matches 1 and 2. Yeah, it looks good. 1 and 1, and 4 and 2, and then this isn't worth 1. This is worth 2. And all of a sudden, that changes the whole graph. All right? So you want to be able to just solve for a and then use inspection as just a check. All right? Otherwise, you could be making an error, especially if the graph is distorted by having a different scale on the a and on the x and y. Right? And here, not so easy, right? Especially when we don't have a pretty grid to count. Right? But it's okay because we can solve for a. Right? So here we have lots of good choices on points. Let's solve for our h and our k. So notice the 3 points in a row. If with a no grid here, they kind of have to be marked. If there was a grid, you'll see the 3 points making a line. See how those 3 points make a line? And if that's all there was, it would look like a linear function. The middle point is our hk. So 0, 0 is the hk. Right? That's our key point there. And I can take any one of these other points, it's not the 0, 0, for my xy. How about negative 8, 6? That's our hk. Right? That's our xy. The second I write it down, I realize my hand is not listening to what my brain is saying. I'm not sure my mouth is listening to what my brain is saying, but my hand was not listening to what my brain is saying. That's our xy. All right, so now we have y is equal to a. Now it's just the cube root. Right? And I'm going to tell you that b is 1, so we'll leave b off. All right, so a times the cube root of x minus h plus k. All right, and so now we will plug in and solve for a. All right, so we have 6 equals a times the cube root of negative 8 minus 0, and then plus 0. H and K are easy to simplify, right? So 6 equals a times the cube root of negative 8. And then, of course, that's just 0. Cube root of negative 8 is negative 2. 6 equals the cube root of negative 8 is going to be negative 2a. And then we divide by negative 2. Right? Negative 3 is equal to a. Once we have a, we can write our equation. Y, or f of x, equals negative 3 times the cube root of x. And we don't need anything else there. So cube root function is kind of interesting because it's so symmetric. Generally, we'll generally assume that's the a that's changing. But just, all right, to mess with you a little bit, what if we had y equals the cube root of negative x? What would happen? Right? So normally our graph, so of course negative 3 could not be our b, but just kind of interesting what happens with the cube root function here. Here's our parent graph, and then we have 8. Oh, I'm going to be right in the middle of it here. Maybe I shouldn't mess with you. But, so I know what, I don't want my Nearpod to go on forever. We can talk about the cube root, what happens if it's a cube root. Square root, so let's just say, how much difference is there between y equals the cube root of negative x as opposed to y equals the negative cube root of x? Take a look and see if both of them graphed and see what they both look like. See how much difference there is. Right? But we can talk about that in class. I should finish our Nearpod. Right? But here, that's clearly an a value, right? Because not only is it reflecting, it's also vertically stretching our graph, right? So our graph is vertically stretched. All right, and so this one, okay, I will now tell you b is not 1, all right? So it's the last one we're going to do. But I will tell you that a is equal to 1. So I'll never give you both of them to solve. Right? But this one is clearly a b. How do we know it's clearly a b? Right? Well, it's reflected across the y-axis, right? And that's b, not a. Right? You affected x, you didn't affect y. All right, so now let's figure out what else we have going on here. All right, so f of x, or y, I'll write y just because we're plugging in x and y. So y equals, and then we have a, well, I already told you a is 1, so we'll leave that part off. So y equals the square root of b, now we need parentheses, x minus h, close parentheses, plus k. Right? Got to figure out the b first. All right. Now we're going to do it by inspection. All right, because b is a little harder to solve because it's in the radical. All right. So let's graph our parent function. Right, and 2, 3, 4. All right. So here's our parent function. Y equals the cube. Excuse me. That's the last part. Y equals the square root of x. All right, there's our parent function. If we reflect it, we have, if we, b is negative 1, then we have this. Right? So here is 2, 3, 4, and 5, 6, 7, 8, 9. All right, so here is, ooh, crazy looking line there. All right, so there is y equals the square root of negative x. That's the only thing that will reflect that across the y-axis. All right, so we know that b is negative. Well, we don't know for b is -1, but we know b is negative. Let's see if we can figure out whether it's negative or positive 1. All right, so notice, let's do the same thing I did on another graph. All right, so this one, the scale is everything's going up by 1s. All right, so 1 up, 1 to the right, 1 up, 1 to the left, 1 up. All right, so we're still holding that 1 and 1. All right, how about over here? All right, so 1, oh wait, I'm sorry, wrong graph. Yeah, of course, that one has b is -1. We got to check the other graph. Our graph. That's okay. Here we go. All right, so 1 and 1 and 1 and 1. Right, and we don't do green because the graph is in green. Don't do red. The other graph's in red. How about blue? All right, so 1, 2, 3. Oops, 1, 2, 3, 4, 2, and then 1, 2, 3, 4, 2. All right, so you can see that it's holding those distances. I know that's a little busy in there. Maybe if I take some things out. Here, we'll just compare the 4 and the 2 so you can see that. And maybe a color that's not up here. How about pretty color, pretty teal. Oh, I guess it's going to be green. Oh, there it is, teal. All right, so if we look here at the parent function, 1, 2, 3, 4, 2, and we look, I'll write that one in another color so you can see it, and we look at our function, 1, 2, 3, 4, 2. All right, so you see they're holding the same rate of change. So it's just reflected over the x-axis, or y-axis, that's it. So we have a reflection over the y-axis. Oh, transpose 2 letters there. Over the y-axis, and no dilation. So that means b is -1. Right? So we know that much. Now we're going to figure out the h and the k, right? And then we'll have our equation. Right? We did the hard part was finding out b. H and k are pretty easy. We just identify our key point. Our key point's right there at 3, 0. So k is 0, h is 3. We just got to be careful when we plug it in. Right? So y equals -1, and then don't forget your parentheses, and then it's just x minus 3 because 3 is to the right, and then you don't have to put plus 0. So our final equation, because we can, instead of putting a -1, we can just make it negative x minus 3, and there we go. There's our equation. We did it. Right? So notice if you leave the parentheses out, then it's going to be y equals, it would have to be y equals x plus 3. Right? So, and then they'll mess with you because you'll be thinking, oh, it's supposed to go to the left. I don't understand. But if you put the parentheses in, it's just like before. All right, I think this is my last one. I'm almost positive. It is. So I'm going to stop there. So bye for now.